SwayamPrabha. Digital India. Educated India.
Let us start this lecture with a thought process. Life is like a river whose flow can be easily channelized for realizing your potential, not stopping it, putting a dam. If you recall that in the last lecture, we basically looked at how to relate the properties. Property means transport properties like viscosity, then conductivity, thermal conductivity and diffusivity to the molecular properties like diameters and other things, right. And what I am thinking now, we will also look at little bit now, and later on we will have to modify it further, because if you recall that we had derived this relationship using a very simple kinetic theory of gases, right. So, if you recall that we had basically derived this formula for the mass diffusivity, right, 2 by 3 and kb q t divided by pi q m half T by sigma square and P. So, this is for the mass diffusivity, right. And if you consider this diffusivity, right, is basically proportional to what? T power to the 3 by 2 and P power to the minus 1, that means inversely proportional to the pressure, right. And if you look at thermal conductivity, right, we had derived as basically this relationship. I had not derived, I had left it. I guess that you might have derived by this time. If you have not, please derive it, okay, which is very simple, right. And this is root over m kbt divided by pi into Cv divided by pi sigma square. Keep in mind this Kb is basically Boltzmann constant, right, and T is your temperature, mass is the mass of the what you call molecules. And in the similar fashion, if you look at K is basically proportional to what? Half, and P power to the 0, that means it is independent of pressure, right. And similar way the viscosity, this like viscosity is basically mu is nothing but again 3 root over m kb t divided by pi sigma square. And the similar way you can find out basically it is power to the half and P naught, it is independent of pressure, right, for the gases. But if you recall that simple theory of kinetics, like simple kinetic theory of gases that we had used earlier for deriving this relationship for the thermal conductivity, viscosity and diffusivity, right. In that case, what are the assumptions we had made? Because there we assume there will be elastic collision and there is no interaction between the molecules except during the collision, right, and those will be spherical in nature. Which one? The particles. Particles means it can be atom, it can be what you call radical, it can be molecule, that is the particles what we consider. But is it really possible that there won't be any what you call interactions, or will it be spherical? No, it need not to be. And also the rigid The molecule won't be rigid, because there will be, of course, there are various kinds of this thing you can consider. One is polar and is non-polar, right. If you non-polar consider, there will be basically the dipole moment will be there if it is a bimolecular and trimolecular, triatomic or biatomic molecules, right. Then there will be interacting with it. Suppose one molecule will come over, then there will be dipole moment, and that will be inducing the other molecules also. So, as a result, there will be what you call a effect will be there. That means whenever they are coming, like there will be some kind of a interaction will be there, because one molecule will be coming closer to another molecule, there will be dipole moment, there will be some kind of a what you call attractive forces, and when it will come very near, there will be repulsive forces, right, which we consider, but in a little different way, right. That model what we use, right, is basically rigid sphere model, right, and that gives something potential which will be, right, and that potential has to be taken care. This potential, if you look at, there are several models, right, for potential functions, right, there are several models to take care of potential between this molecule during interactions, right. There will be potential function has to be taken. There will be some force field, right, in the molecules, and there are several models are being given by the various people. Models are given, right, till date, and several more model will be also coming up in future. But what model we had considered earlier is this one, that is what you call types of models, right. There are several types. We had considered rigid sphere, and there will be also what you call square well model, and there will be what you call Sutherland model, Sutherland, some people call Sutherland model. There will be Lennard-Jones model and Buckingham. There are several of them. What we are considering till now is the rigid sphere model, right. And in that case, what we will be looking at, basically force will be dE, this is the potential, right, by dr. Dr is the basically radial direction you are talking about, right. Now, we will be, among all these things, we have already discussed about rigid sphere model. Till now we have considered, we will be considering the Lennard-Jones model, because that is being used very much in the combustion problem and it is easier to handle. Okay. But rest of the things is not only this what you call 5 of them I have jotted down, but there are several models, like if you look at this molecular theory of gases by Curtis and Bard and then Hirschfelder, you will find that several models are there, right. So, if you look at the model, what we had considered is basically this is the potential rigid sphere model, right. Which is considered as, let us say, this is your repulsive forces and this is your, this is basically E potential, right, energy. This E for stands for energy, for potential, and this is the R direction, and this distance is sigma. Sigma is the diameter of the sphere what you are considering, and this is your repulsive forces and this is your attractive forces. That means it will be 0. What is the meaning of that? E, if I look at rigid sphere, is equal to infinity when R is less than sigma. That means repulsive forces will be very high, right, when it is r is less than sigma, smaller than that, and this will be 0 when r is greater than equal to sigma. That means it will be, I have put it here, but actually it is 0, okay, just to differentiate, because if I say this is 0, right, this I am putting just to make a difference, otherwise it is 0, okay, are you getting? But if you look at the real situation, this is ideal situation, ideal gas, but in real gas what you will consider is basically there will be repulsive forces A divided by R, right, you can say this is power to the 12, right, B power to the what you call R 6, this is the attractive forces. Keep in mind this 12 and 6, right, this will be, and when you sum it up you will get, this is the red line, this is the actual potential what will be coming, right, the red line, the total together, it will be together. Now this is if you look at this diameter is basically sigma, the distance between two particle is r, right, is considered. And keep in mind that this is basically, if I consider this is your sigma, right, and this is I can consider, right, or this may be here epsilon, right, epsilon is, sigma is what, sigma is basically diameter of particle and sigma is the depth of intermolecular potential. So, and this is basically known as what, Lennard-Jones 612, right, potential. Keep in mind that I can take this, instead of 612 or 6, I can take some other thing as well, I can take anything as a matter of fact, EILJ, right, is equal to 4 epsilon sigma by r 12 minus sigma by r 6. This is the potential what is being considered, right. And as I told, this 12 and 6, you might be thinking like, is it the right model or not? It is not, it need not to be, because that depends on the kind of molecule you are handling, okay. But by and large people found this is good, and also it is convenient to handle mathematically, that is why people put 12 and 16, okay, that is the reason what was given, and I was surprised to know that, isn't it, like that means there is a lot of scope for you people to improve on this model, okay, and we are considering, because we are happy with this and within the error what we will be getting, right. So what we will be discussing only this Lennard-Jones 612 potential, right, or you can say 12-6 potential, right, so that is okay. And we will be seeing that how it is. For that we need to look at basically this data, right. You can either get that from the some data book, or you can have some inversely you will find out the diameter of the molecules, suppose some new molecules kind of thing. And this r is the, as I told, it is the distance between, r is the distance between two what you call participating particles, right, between two participating particles. So let us look at this, if I want to get this thing, then naturally I will get some molecular data sigma, right, and that will be it is given some of the species H, O, S2 kind of things, and these are the diameter of the particle, which is order of nanometers, right. And this epsilon is the depth of intermolecular potential, and this Kb is your Boltzmann constant, right. So, it is given, all these data you can get from a table, right. By considering Lennard-Jones model, like potential model, right. We can derive, like these things, but I will just give you the final, this answer for the diffusivity, that is for diffusivity. Relationship for diffusivity, right, di, it can be 3 by 8 pi m kb t root over divided by pi sigma square omega 1 comma 1 star, right, and 1 over rho. So, if you look at it, is similar in nature, right, isn't it? Like Kb, the Boltzmann constant is there, T is the temperature, right, and sigma is your diameter of the molecule, but there is a one term which is coming, this is the term, and that is known as the reduced collision integral correction factor. The sigma is basically reduced collision integral factor, right. And this is why it is given, because it is given to include the effect of real gas, right, that is the thing. It is to 1 comma 1 star, right, star, this is star. And if you look at, of course, there is some relationship for that. There might be several relations for this reduced collision integral factor. I am just giving you one of them, right. Let us look at this. This will be basically this collision integral factor is a function of T star, right. So, if you look at this T star, right, this T star is equal to basically Kb by T into epsilon. If you look at this Kb by epsilon, already we can get from table, we have seen that just now, like So, and epsilon is what? Your well depth, the depth of that valley in that this thing, right. So, therefore, this you can get, and keep in mind that it is changing with temperature, it is a log and log plot. This is omega 1 by 1 star, and this is being used for the generally diffusivity calculation, and omega 2 by 2 star is used for viscosity and the conductivity calculation, which we will be doing, and there will be some difference in that, but it is similar in nature. And for binary mixture, right, so consider, let us say this is for binary mixture, diffusion coefficient, right. Equation 1 becomes, right, DAB 3 by 8 root over pi kb t mr divided by pi sigma ab square 1 comma star. Now this is basically a function of this thing into rho. So if you look at this sigma, gamma 1 comma 1 star, this is reduced collision integral of, you can say, this thing is equal to, basically I can use a semi empirical relationship TAB star minus 4.9 plus 1.91 TAB 1.58 power to the 0.1. Now this is also TAB, okay, and this TAB I have already told you, but let me again tell you that T star AB is equal to KB by T by epsilon AB. What is epsilon AB? Epsilon AB is equal to epsilon A, epsilon B. You know that A is a molecule, B is another molecule, okay, are you getting? And then this MR is the reduced mass, which already we have defined earlier. Let me write down a MA MB divided by MA plus MB, right. And what is sigma AB? Sigma AB is equal to sigma A plus sigma B divided by 2. This already we have discussed, I am just restating again. Now to, if I say this is equation 2, to simplify that equation and in a manageable format which will be easier to use, we can do that. We can actually put these KB values, pi values and kind of things, and express this density in terms of pressure and temperature kind of things using ideal gas, because if you look at the real gas is taken care by reduce reduce collision integral, which takes care of the effect of real gases. So the rest of the things are pertaining to ideal gas, are you getting? So therefore I can write down the equation 2 becomes by simplification equation 2 DAB 2.662 10 power to minus 2 TQ half molecular weight of A plus molecular weight of B molecular weight of A into I can say multiplication MWB, right, divided by P sigma AB square star, and this will be in unit of meter square per second. And keep in mind that P is in bar, P is in bar, P is the pressure, right, in bar, and T is in Kelvin, and molecular diameter sigma, this is molecular diameter, it can be A, it can be B, I am just writing that way, meter is in nanometer, and MW is in gram, okay. So this unit one has to take care whenever you are using the, let us say, equation 3. Equation 3 whenever you are using, be careful about units, otherwise it will be all topsy-turvy, means it will be complicated like it will be something garbage you will get number wise. Are you getting a point? So generally people use this one and then be happy with that, and we may do some calculation just to have a feel. Now having done this thing, question arises, we may get the diffusivity for a particular mixture with respect to another we may get the diffusivity of one molecule with the another respect to another molecule. But however, in combustion problem, right, we will have to handle mixture of gases, that means mixture of several molecules. Now, how we will handle that? Because if I will go on doing that, then it will be, life will be very miserable. Let us say I am having 23 species, I mean 23 diffusivity allowed to carry, and then others will be also moving with having different diffusivity, isn't it? How we will take care, that is the important, because we will be learning how to take care of mixture. So, for determining the diffusivity mixtures, we can use certain empirical formula, right. Of mixture of other compound or other species, right. What we are doing, we are basically looking at diffusivity of right, of particular species with respect to other species, right, of mixtures, right, in a mixture will be basically DIM is equal to 1 minus YI divided by XJ into Dij, where J is not equal to I, where Yi is the mass fraction of ith species and the Xj is the mole fraction of ith species. Of course, the Dij is the binary diffusion ith species with respect to what is that? J species. And keep in mind that you are basically calculating in the diffusivity of ith species, okay, determining diffusivity of ith species in a mixture, right, in a mixture of other species. Are you getting? So, and if you use this thing, there will be some error, okay, and that errors will be in the range of something around 10 to 15% kind of thing. So, if you use this, because this is, let us say 4, right, and the errors, if we use this because formula and also other whatever we have done till now, the errors will be is around something 10%. So, we will stop over here, and then in the next lecture we will be discussing about how to handle this other properties kind of thing, right. Thank you very much.